let's do a problem using work and energy. So the whole concept of work and energy, if you have your topics list for this week, okay, you have that topics list, you'll see that it says power, vertical problems, upwards, and horizontal problems with power. We'll do some of those. Potential energy, gravitational potential energy, elastic potential energy, spring energy, work energy principle. In fact, the work energy principle, I've got like 2 dots on the left, 2 dots on the right. Dots around it, dots around it. Major important. The most important equation in first semester physics, I would argue, is F is equal to ma. Really? Come on. Who's going to argue with me? You? No, I didn't think so. So that's the most important equation. But the most important concept is as follows. Work. Try again. Work is equal to potential energy is equal to kinetic energy. And I'm going to throw this one in, is equal to Q, which is heat, even though in Physics 1, first semester physics, we're not going to be focusing on work. That's semester 2 stuff, thermodynamics. But it is in this, I like putting it in here because these all have to do with energy and energy transfer. This is called the work energy theorem. If you have work, you can do and create energy in something else, potential or kinetic or both, by doing work. They can be transferred from one to another. Essentially, it's a conservation of energy. I guess that's the most important thing, because basically all physics deals with the transfer of energy from one thing to another of various kinds. So, work, think about what we had for units. Work, the unit was a joule. We didn't show you this with the potential energy equation. I'll do it now. Potential energy is mgh. Potential energy is mass. What's the unit for mass? You all know, kilograms. What's the unit for g, little g? It's an acceleration. Meters per second squared. What's the acceleration for height, which is a distance? Okay, remember MKS, meters. So if I were to look at this, this is kilogram meter per second squared. That is a Newton. And what do we have? We have a Newton times a meter, which is a Newton meter, which is a joule. It's a joule. That's not a very good J. That's better. So this is joules. Kinetic energy. Kinetic energy, our equation, is 1/2 mv squared. 1/2 mv squared. Let's look at the units. Unit analysis. Mass is kilograms. Velocity is meters per second. We're squaring it. So that's meters squared per second squared, which is kilogram meters per second times another meter on top. Hey, Hokey, Pete, and Joe. We got ourselves another joule. So all of this stuff, and he is, we won't go into that derivation, but you remember from chemistry, it does come out to be a joule. So these are all the same. One is converted into another, conservation of energy. And that's important to solve physics problems when it comes to work, power, energy, because we can now use this concept in order to do these and apply this concept to solve particular physics problems. And let's go ahead and dive in and do that. I loaded in for you this week, okay, into Canvas. We have level 2 problems, level 3 problems. For the next 2 weeks, we'll use this worksheet and to go through. Trust me, you're going to want to know how to do these problems. All right? You're going to want to know how to do them. Let's, however, before we dive into those specific problems, I'm going to do one problem that's really important. Muy importante grande is this following problem. I call it the Grinch problem. The Grinch. Yeah, the Grinch, like in Christmas, like in Jim Carrey / cartoon version, which, by the way, is better. The cartoon version is better. Jim Carrey, good job, but sorry, cartoon better. So what are you talking about? Well, let's say we've got the Grinch. Now, this is actually the Grinch. This is a mountain. It's Mount Crumpet. We all remember it's Mount Crumpet, 10,000 feet up on the top of Mount Crumpet. Okay, it was 10,000 feet. If you know your Grinch, you know what I'm talking about. So this is 10,000 feet above our base here, which we're going to put Whoville. Whoville is down here. So here's Whoville. Whoville had some weird-looking buildings, a couple round windows, and of course down here is little Cindy Lou Who, she's got antennae on top of her head. Hey, who's judging? Okay, there's nothing wrong with antennae on top of your head. Okay, don't be judging. So now what we have is the Grinch 10,000 feet up. Now 10,000 feet isn't going to work with physics, so we have to convert that into meters. Did it for you. 3,100 meters-ish. So it's about 3,100 meters. 3,100 meters above Whoville. That's our reference point here. Now the Grinch is in a sled at the top of Mount Crumpit. He's sitting on top of the sled. There he is. We'll give him a nice little winter hat there. Here's a cute little hat. And of course he has his dog on the sled. We all remember his dog. Yes, Max. Thank you. Max. So here's Max. We'll draw our generic dog, stick figure dog. Okay. And on top of that, he had one little antler, right? The Grinch had a cut off because otherwise you went. All right, so there he is, Max, Sled, and the Grinch. Max, Sled, and Grinch at the top of Mount Crumpit. We got to give them a mass because we want the potential energy, right? We want to know how much potential energy they have. Actually, I didn't even told you what the problem is we're trying to solve here. What we're trying to solve is for the following. How much potential energy, kinetic energy, and velocity will the Grinch have as he triumphantly enters into Whoville, and how much potential energy, kinetic energy, and velocity does the Grinch have at the top of Mount Crumpit? So let's figure out the amount of each potential and kinetic and velocity at the top of Mount Crumpit and Whoville. Okay, so now, these, I can get 2 of these done right away. What? You're not even doing any math. You're so smart. No, I mean, come on, you know this. How much kinetic energy do we have when we're sitting at the top of Mount Crumpit? We don't have any. We're not moving yet. Remember, kinetic energy is the energy of motion. So we don't have any. So I don't have any kinetic energy, which means I'm not moving, so I don't have any velocity either. So that's a big fat 0. So I don't have any. That's pretty easy. Potential energy. Now that I have. I've got some gravitational potential energy. I've got some MGH. So let's figure that out. How much potential energy? Okay, I need the mass. So we need the mass of our Grinch, Max, and Sled. I don't know. Let's give them a mass of 400 kilograms. A big, heavy sled. Max isn't very heavy. The Grinch, I don't know, maybe 100 kilograms. So, but big, heavy sled. Because you saw that sled, right? You remember that thing was huge. Got a lot of bundles on that thing from Whoville people. Right? So 400 kilograms. So let's go ahead and do MGH. So 400 kilograms times G, which we're assuming that G, even at the top of Mount Crumpit, we're on the Earth, we all know where the Grinch lives. He lives in northern New Hampshire. Okay, I've seen him. I've been there. Okay, Whoville. You've been? Yeah, been there. So it's 9.8, so gravitational acceleration. And height, well, we're 3,100 meters above our reference point. So if we do the math on this, that's going to be a big number. I mean, go ahead, look at that thing. You can see right away, it's a lot of bigness to this number. So 400 times 9.8 times 3,100 equals 1, 2, 3, 4, 5, 6, 12 million. 12 million joules. 12,152,000 joules. That's 12,152,000 joules. Whoa. Well, I remember a joule, if you do remember, a joule is actually a very small unit. It's not a very big unit. It takes 4.19 joules equal 1 calorie, and a little calorie, and it takes that's the physics, chemistry calorie, and it takes 1,000 of those equal 1 food calorie. So that means a joule is not very big. But if you got 12 million of them, it's starting to add up. It's a lot of joules. Okay, so there's a lot of potential energy there. Okay, so now we have figured out how much potential energy, kinetic energy, and velocity we have at the top of Mount Crumpit. Now I'm going to take this 12,152,000 and solve for one of these at the bottom, assuming no friction. Now, that's a huge assumption, but let's assume for this problem there's no friction between the sled and the runners in the snow. That is the music, by the way, as the Grinch is going down on the cartoon. Yes, it is. As we enter into Whoville, we've got no friction. Well, that makes the problem a little bit easier. That's a lot easier. What would be the potential energy of the Grinch at the level of Whoville when he's entering into Whoville? And Cindy Lou Who, you better get out of the way. Okay, you're going to get run over. Cindy Lou got run over by a reindeer. There's a song. I've heard it. Okay. So Cindy Lou Who, get out of the way. We have all of that potential energy is now gone because we're at the level that we were measuring our potential energy from. So it's all gone. P.E. Whoville, 0. Where did it all go? I don't know. Maybe you went to the store to buy some toilet paper. Really? No, it all got converted. It all went from potential energy at the top to kinetic energy at the bottom. Remember earlier we started this whole thing by W equals PE equals KE. That is the work energy theorem, meaning that one can be converted into another, and all the PE at the top becomes the KE at the bottom. So our KE, assuming no friction loss, is going to be 12,152,000. That's the most important concept of this entire problem. It's actually not a hard one, but it's really important if we're going to move through these problems. We got to know this. Work energy theorem. Potential can become kinetic. In fact, if the Grinch were at the bottom of the mountain, he'd have to get to the top to give himself potential energy, meaning he'd have to do work. He'd have to do work to get to the top. Then that work became his potential. Then he'd rise back down the hill. That potential becomes kinetic. And we have this big cycle of awesomeness. Last thing to solve for. How fast is he going at the bottom of the hill? Now we're going to solve this using energy relationships. In fact, all the problems in this unit that we solve for velocity, if we have to solve for velocity, we're going to use energy relationships. Now we could use the big three. Remember the big three, our kinematics equations? We could figure out, knowing gravity, knowing the height differential, knowing D, we could figure out initial velocity is 0. We could solve for VF. No, no, no. You see, on your next assessment in a few weeks, I'm going to ask you to do one of these problems, and you have to use energy relationships. So show me how to use energy relationship and solve this, not the big three. All right, well, how would I do that? Well, the only equation out of these that has velocity in it, not you, you're F times D. Not you, you're mgh. Nope. You. 1/2 mv squared. This has velocity in it. So I'm going to use the kinetic energy to solve for velocity. In fact, we just said that our kinetic energy is now 12,152,000. Let's set that equal to, because KE equals 1/2 mv squared, set that equal to, get you out of the way, 1/2 mv squared. All right, let's plug in. All right, Cindy Lou Who, I'm getting rid of you. Sorry. All right, so our velocity, so let's see, about 12,152,000 equals 1/2 our mass of 400 times v squared. Solve for v. So half of this is 200, half of 400 is 200. So divide 200 into 12,152,000, then squared, so we don't want v squared, we want v, so take the square root of that. I'm going to knock a few zeros off here. Okay, so 121,520 divided by 2, and then take the square root of that. Let's crank that bad Larry out. Okay, divide by 2, second function square root, second function answer. Let's see, 121, 520. I had the wrong number. 121. Divide by 2, second function square root, second function answer. and we get 246.5 miles per hour. I'm going to make that 247 miles per hour. Again, 247 meters per second. 247 meters per second. Now, if you remember earlier in the course, I said, how do you roughly figure out how fast meters per second is? Double it and add a little bit. Well, this is actually pretty fast, so double and add a little bit more. If I double that, I've got, I'm over 500 miles an hour. Okay, I'm well over 500 miles an hour. Cindy Lou Who better get out of the way, or she's going to be a little pink vapor cloud. That's it. It's all a pink vapor cloud. She's going to get vaporized if she's not out of the way of that. All right, so 247 miles an hour. We ain't playing. Grinch ain't playing. Grinch ain't going to play. Okay, he's coming in. He's coming in. Coming in hot. All right, so that 247 meters per second, I keep saying miles per hour, meters per second, fast, over 500 miles per hour. That's, of course, assuming where we have no loss of friction. We'd have a lot of friction, which would, of course, we would not come down at over 500 miles an hour, but we'd still be coming in pretty fast. Okay, so the important thing here was the potential becomes the kinetic, and we can solve for velocity using kinetic energy because it has V in it. Okay, one other thing I will mention. Some of you might know this. Some of you might have noticed this, and the studio audience out there might know that at the top of the hill, my PE had an M in it. At the bottom of the hill, my KE also has an M in it. Let's look at those because my PE became my KE. PE is mgh, becomes KE 1/2 mv squared. Those masses are the same, they cancel. So it doesn't matter what we gave the mass of the Grinch Maximus sled. I could have given him 8 billion kilograms. 8 billion kilograms, whoa, that's a lot. I don't think I could lift that much. Yeah, it doesn't matter because we would still end up going the same velocity at the bottom of the hill because the mass is irrelevant here. It would actually cancel out. So, yeah, kind of cool, huh? It's cool because it was snowing in Whoville. It's cool.